Okay, so what we saw last time, there was a double angle formulas such as a sine of 2. I put alpha, it's easier to write than theta. It's going to be 2 sine cosine. See, there's a whole bunch of formulas that I know very kind of difficult to comprehend when you see them first time, and there's lots of these formulas. So I guess the way to go is just try to redo the same exact exercises again that I try to do for you, and that way we can actually maybe do this. Somebody can't hear, so I guess check computer volume. That's standard issue. So anyways, I hope other students can hear me. So looks like these two key formulas is what we observed, and I guess there'll be another one that deals with tangent of 2 theta. And if you remember how the tangent of sum of two angles looks like, it's a tangent added, so that's how twice appears, and then tangent and tangent multiplied, so that's how the squared appears. So I guess that's another pretty straightforward formula that comes right out of tangent of sums, and that's the one that we again don't have to remember, but just be aware that if you have a double angle, then you can always turn this to single angle identity. And these are useful when you have problems that mix double angles and single angles, usually when you're trying to solve equations. So let's, it takes a little time for it to move to the next pages. So looks like with this, I can do a couple of exercises now. So we already did with sine or cosine, so now I can actually try to deal with the tangent or with its friend cotangent and so forth. So please let me find one here with double angles. I need something with 2 thetas. Problems like 70, for example, or something similar to it, maybe 77 has tangent of 2 thetas. Let's do it. Solve equation 77. So they say here tangent of 2 theta. So when I see tangent of 2 theta, I start wondering, should I really use this formula, or it may be a little bit too much? When I look at the rest, it's sine and 0, so maybe instead of tangent of 2 theta, I can try something like sine over cosine. So tangent of 2 theta divided by sine over cosine, right? So this will be one that I start with. Then 2 times sine theta is going to be another piece and is equal to 0, right? So our goal in all of these exercises is always to factor. So I can factor sine 2 theta right away out. So I'm going to get the 1 over cosine of 2 thetas plus Actually, I can't. Sorry, I wasn't careful because I need to do one more step, right? Before I factor, because it's double angle. You see why I can't do this? Because this is 2 theta and that's adjusted theta. So my goal is not to do it like that. That's a bad idea. My goal is to factor out after I use the formula here. So after I replace my sine 2 theta with a 2 sine cosine, 2 sine theta times cosine theta. And then I'd be able to factor something out. So let me rewrite that like that, and then I'd be able to take out the sine theta. Let's see. Well, you can also take out 2. Okay, I can do that. Now we ended up with a cosine theta. And now question is, what should I do with the denominator? Because it's going to be also double angle, right? And it turns out, since I see cosine, then maybe I write everything using cosine, right? So instead of using this formula, I could actually say that this is the same, since of sine squared. Remember, if we use squared, sine and cosine equal to 1, right? So instead of sine squared, I get a cosine squared, and then I subtract from it 1 minus cosine squared. In other words, it'd be cosine squared twice, subtract 1. So right away, I can always get the cronies of this formula with a double angle, with cosine of double angle. So looks like it's slowed down a little bit again. So I just want to show you these. We saw them last time, and today I want to use them again after this particular exercise. So let me just go to the beginning of this section where so here it is, the last expression. See, it's always good to either write with only sine or with only cosine. So I hope that this is what we can utilize now. So plus 1 is left after we factored out 2 sines. And this product is equal to 0. So I already know that either sine theta is 0. Like I say, Alex, what about 2? That makes no difference when you solve equation. Or that other piece is 0, which is what we have here in the parentheses. Well, to work with these parentheses, now I need to get a little bit more room, and I'm going to write it then separately. So or cosine theta over this 2 cosine square theta minus 1, right, is equal to 0. So maybe I'll write it here, because then I'll have to copy it again. There's a little room that I can utilize. So cosine theta over 2 cosine squared minus 1. And here's plus 1 is equal to 0. So there are 2 of them. But then I start solving it. So I put this as a minus 1 on the other side. And then I can multiply both sides of this by denominator. In other words, it'll be minus 1 times this expression. Why? Well, a clear denominator, right? Use proportion rule, or you can say you just multiply by the same exact parentheses, the left side and the right side of your equation. See, it's involved lots of writing. You really want to get plenty of paper here. So when you distribute, you're going to end up with, let me get another color. So -2 cosine squared and +1. And now I'm going to bring it all to the same side. So finally, I'm going to get like quadratic equation. So it'll be 2 cosine squared and the cosine by itself, right? And also +1 goes as a -1 to the other side. You see, it's really heavy algebraic simplifications in this section. But that's good. So now we solve this as if we had quadratic. So 2 cosine theta times cosine theta. So I factor my first term, which is 2 cosine squared, so cosine times cosine, and factor last term. So I factor 1 as 1 multiplied by 1, and now one of them should be negative, right? So which one should be negative? Well, looks like since positive is in the middle, then the smaller should be negative and larger should be positive. You say, why did you say this larger? They're both ones. Well, the product here is cosine, and product there is 2 cosines. So when I collect it, it'll be just 1 cosine. So we get another equal to 0 expression. So this is nothing here. So we now set each of these two equations separately equal to 0. So either 2 cosine theta, right? I'll write it a little bit slower so you can better see what's going on. So, and cosine theta +1. And finally, we end up with two more equations to solve. So one of them is cosine theta is -1, and the other will be cosine theta is a half, right? 1/2. So there are actually three pieces that we care about solving this exercise. See, it really required a little bit more room, but well, problems here. If you can solve this equation, you can solve any equation because this is the one that we can definitely do. So anyways, the 2 makes no difference. So sine theta is 0. And what will be a solution? Well, I need to somewhere find a little bit of a room. So maybe I'll clear this blue stuff above. Okay. So I'm going to get the circle pictured, and I'll put all solutions on the circle, and that'll be good enough. So looks like here's my favorite little friend, unit circle. So now on this unit circle, what are the solutions for the sine theta equal to 0? Well, sine is equal to 0 will be for that point and for that point, because sine is x coordinate. What's the solution for the next one? The red one, cosine is 1/2. So cosine is equal to 1/2. That's on the x-axis. So there will be 2 points. They correspond to angles pi/3, right? Because pi/6 will be square root 3 over 2 little one. And that'd be negative pi/3, but I'd rather say it's going to be 5 pi/3. So that's for 1/2. Because I'm trying to get, as usual, on an interval from 0 to 2 pi. And finally, the last one, cosine theta is -1. Well, look at this. Cosine theta is -1 is in this same point. So that is included in the case of the first one, when sine is 0. Cosine could be either positive or negative. So here's my set of solutions. Pi, 0, and those 2 more points on the unit circle. How about that? So I just applied formulas that we have here, and well, these exercises, of course, if you like them, then you can definitely be good at calculus, because there we have all kinds of algebraic procedures that being involved. Now, here's the key step that follows from my formulas. So the next part of the story, let me get a little bit of a room for this. So I want to clear all of this little by little. So first two formulas above for sine of double angle and cosine of double angle. So you just look at the one that I produced for you here. In other words, let me write it again. The cosine of two of these, they have theta, so I put theta, is equal to what we just ended up with, right? 2 times cosine theta, alpha theta, whatever you like to call it, doesn't matter. So from here, I can isolate cosine, and this is going to look like that. Because if you add 1, you bring 1 to the other side, it'd be plus 1. And then since you have 2 of these cosines squared, you just want to divide both sides by 2. So there'd be just 1 cosine squared. And you got this form. So similarly, we get another formula for the cosine of double angle. And this is 1 minus 2 sine squared. You can produce it analogous way. You get the first one that you just utilize, instead of first cosine, you put 1 minus 1 minus sine squared, and that's how you get 1 minus 1, and then another 2 sine squared. And this gives you a way to produce sine. So once you have those, you can extract square roots on both sides, and that's how you get sine of theta. So it's either 1 minus cosine or 1 plus cosine. That's for cosine. So let me maybe better write this slowly, because this is, I think, a good practice for anyone, just to see how all of these formulas are arising, because they're analogous to the exercises in the book. So you can do another exercise, and that'd be pretty much the same process to basically prove identities, just like proving these little formulas. In other words, so we just got that sine of theta was, I'll write it again, square root from 1 minus cosine of double angle over 2. Again, remember, it could be either positive or negative. So it could be either positive or negative. I don't want to say plus minus, because it's either or. It's not both and plus and minus. But that's how it works. And analogously, from the second one, I can say just a cosine will be plus or minus a square root from that 1 plus cosine of 2 theta. Please notice that they're kind of similar. In one, we have 1 plus cosine, and in the other, we have 1 minus cosine. And it's all because of this particular double angle identity. That's the key part. So if you look at the next group of these formulas for half angles, notice here they are. Sine of alpha over 2. So what you do is, instead of theta, you put alpha over 2. That's so-called little substitution. And if you multiply both sides by 2, you get 2 theta, which is equal to alpha. In other words, in this formula, you can replace your theta with alpha over 2. So you just do a replacement. So on the other side, it still be this plus or minus square root of 1 minus cosine. So now cosine of what? Well, cosine of 2 theta. Well, 2 theta is same as alpha. So they just, I guess, changed their angle just to show it's the same formula, but it could be used for so-called half of angle. And analogously for the second one. So if you, again, write this down, such as a cosine alpha over 2. It's again, could be plus, could be minus, and it's a square root from 1 minus, oh, sorry, plus. Now we have cosine of alpha. So they really want to show it's over 2, so it's like half angle formula. That's why we have this. Well, this is the, I guess, another pair of formulas. Actually, they have one for tangent as well. If you divided sine by cosine, you probably can see that 2 will cancel because it's analogous. If you put sine on the top, which is 1 minus cosine, and the cosine on the bottom, so it'll be 1 plus cosine, right? And a 2 or 2 will cancel. So tangent, I guess, is just coming out from those 2 formulas. So I guess that's plenty. So I don't think I want to overload you because it's too much. I know there's lots of formulas. But the point of story that now we can deal with half angles as well. So I'll do just a couple of exercises to show you applications of this. Like, for example, problem number 19 that talks about sine of 22.5. So please notice that 22.5, if I call it as alpha, actually over 2, then alpha will be 2 times that angle. And when I multiply this angle by 2, it's going to be 45. So I'm going to use that one. So I'm going to use this square root of 1 minus, and now it's a cosine of 45. So it is pretty straightforward because you're just going to need to recall what cosine of 45 degrees is. And again, it's not ever going plus minus. It's always either plus or minus depending on the quadrant, just like we already saw before. That's why 45 degrees, an angle of, let's get some room. Half of it will be half of 45 will be in the quadrant number 1, right? So when we're in the first quadrant, well, sine is going to be positive and cosine will be positive. And just to make sure I can again draw my little friend unit circle, because it's always ended up being unit circle that we can look at and right away get ourselves an idea. So if you get here 45 degrees, right? Or pi over 4, then half of it will be the angle that we're working with, 22.5. So please notice that we're looking for its sine someplace here, and the point is it's positive. And that's why you don't need minus, you just keep it positive. Of course, we don't put plus in front, but still. So anyways, what do we get? We get 1 minus, it's a square root 2 over 2, right? cosine of 45. Do you still remember that? So for 45 degrees, if you check page, the last page with formulas, we're gonna have a cosine 45 is a radical 2 over 2, and the same as a sine, right? It's radical 2 over 2. See, we going to stay with these formulas till the end of this class. So I hope that some of you already feel familiar with this unit circle. And if not, go to the last page and double check. So what bothers me here? 2 in denominator. So I'm going to multiply the top by 2 and the bottom by 2. And I also have to multiply here by 2. So entire numerator and entire denominator by 2 just to cancel that little denominator. I guess that's the fastest way to do this because now we get the answer. What do we get? 2 minus 2 square root 2 on the top. And what's on the bottom? 2 times 2 is 4, so I can extract the square root is just a 2. Look at that. This is the expression with exact value. Of course, if you put it in the calculator, it's going to give you something approximate. So you're never going to see this type of expression, right? But that's what they want. So we use square root 2 over 2 and then simplify it a little bit. Yeah, this section is involved with lots of these little algebraic details, but as I said, it's always going to be lots of simplifying in this chapter, so should get used to it. So what's going on here in the next group of exercises? Let me try something with half angle identity, like 32. Well, I guess they're just trying to create some exercises that may look unusual. So if you actually don't panic and don't hurry, and if you see what function they're actually talking about, so function is a sine, so it's actually a sine of a half angle. That's what they want. It looks like they want you to use the formula that we just utilized already, which is here. So they show you the actual picture, and on that picture, they want to know angle theta over 2. So where's angle theta? Looks like they want to use this one. So they actually put 2 pictures in this set of exercises. Somehow they try to combine 2 different things together, which is they have absolutely no relationship to each other. And I think it's a little bit confusing because they should have had one group for the first picture and the other group for the second. So that way it will be easier. But anyways, the point of story that if angle theta is here, then theta over 2 will be here. And that's all we care about because now we know that we're in the first quadrant. So we don't again use plus minus, we just use plus. So the point is that we're gonna have to use positive square root from this 1 minus cosine of theta. And this is divided by 2. So right away, I turn it to the angle theta because we have the information about angle theta, I guess. So we're going to be trying to decide what is going on. So now how to decide what is going on here? Well, for this angle theta, I need to find its cosine, right? So how can I find the cosine of this angle theta? Well, again, if I look at the picture of my unit circle a little bit closer, with angle theta, which is here, right here. So now we start working only with angle theta. We figured out what we want. It's right here. So we wanna now decide what is this minus cosine of theta is. How can I possibly find it? Well, point on the unit circle has a cosine right there, right? And it's negative. So we're gonna need to find this point here, but there is a little bit of a problem. The radius is 5. So it's not really a unit circle. It's actually blown up 5 times. So the circle they work with is big. It's okay. Once we have idea what actual cosine theta is, we're gonna multiply it by 5. And that's how we get 2, 3, 5. So it'll be 5 times. So we'll multiply by 5. So here they say we have point with coordinates A and 2. Okay, so what does that mean? Well, I think it means I need to get some room, first of all. So I'm gonna clear this mess a little bit. So this is not what we would use. So let's put maybe that picture again because it's all on the way. So I'm gonna be making a bigger picture again. That big, I had it red, so this is big red one. So on that big red picture, they say angle theta is here. And the coordinates will be numbers A and 2, right? So A is here and 2 is there. That's what they gave us, right, on the picture. Okay. So how do I find my cosine? Well, the cosine will be coming from that little green circle, right? Which is little one. With radius 1. So that one has radius 5. So what I need is to divide by 5. So this is going to be a put arrow, don't fit. A over 5. Actually, this is 2 over 5. So y coordinate divided by 5. And that will be A over 5. Because they're 5 times smaller. So basically, I just need A over 5. So what they need to do here? What is their question? Use the figures to evaluate given expression. So what is A here? Well, use Pythagorean theorem. See how many steps we have in this little exercise? So I need to not hurry, but just move it little by little. So I need A over 5. See, I'm starting to erase in this lower corner and my picture above is being damaged. It's a zoom update. That's nice. They like it. I'm gonna try to contact them, but somehow I need to see how I can pull this thing out. But so I can send them the recording. So this is a big circle. Somehow like that. Like that. Anyways, so it looks like I have to use the fact now that we have x squared plus y squared is equal to 5. And then I need to also utilize the fact that instead of x, so here's my point with coordinates A and 2. And that's my point that corresponds to pair x and y, right? So this enables me to actually find A. So that's kind of a totally different thing. But I don't know why they combine so many things in one. I guess just to make you enjoy it over weekend, I guess. So instead of x, I put A. Instead of y, I put 2. So whatever this is going to be, it's a 5 squared. Oh no, they gave me 5. So actually, radius is a square root of 5. Oh, I should be careful, so because that's divided by square root of 5. Because radius is not 5, it's square root of 5. Okay, it's good to be careful. So anyways, looks like A is going to be 1, right? Because it's 5 minus 4, so there's 1, which means that A is 1. Maybe positive 1, maybe negative 1. In our case, A is negative 1. So if A is equal to minus 1, according to this case, because we are here on the left from 0, so we actually need what? Well, we need this. A over 5, that's going to be our cosine. Cosine of angle theta is A over 5 over square root of 5, sorry. Square root of 5. Let me write it nicer. This is hard to understand that this is square root of 5. And we're done. Because since it's A over square root of 5, then we can also put negative 1 instead of A. So it's minus 1 over square root of 5. Then we finally can write the answer here. So we go with, first of all, I take away this big red. Don't need it. So I found cosine, so I just plug in, instead of it, this minus 1 over square root of 5, and it will be done. It is too much. I know there's too much, but if one can follow this solution, I guess you need to get a piece of paper and pen so you can write these steps, because it's really a lot. Trying to square root of 5 here. So this will be good enough, but again, they will probably make you simplify this, right? So they always like to simplify. So I can also try. So I'm going to multiply by radical 5, the top and the bottom. And this will give us the result. Ooh, that's just too much, I think. So square root of 5 will put on the top. Square root of 5 also needs to be distributed over the other piece, and square root 5 is on the bottom. And this is all being done to cancel this denominator square root 5. And looks like we have the answer. So inside the square root, I got a radical 5 minus 1, or minus and minus is plus 1, over 2 roots of 5. It is pretty nasty. That's the conclusion. Maybe I should stop torturing you with this, because it is really a little bit too much, and I don't think I put this on the exam, because we already had this trig stuff, arc functions on the exam, but that's the way the material is. The course material, I think this is probably one of the least pleasant sections of chapter 7. And the good thing is that we don't do 7.7, because these formulas are pretty much never going to appear. But again, maybe once in a blue moon you will encounter exercise that deals with these formulas, because they're not hard, they're just kind of no use. So you can come up with more formulas, but I don't think you will really need it. So I think at this stage we'll be done with this tedious chapter 7, and next time we're going to look at the following chapter 8. Just want to take a sneak peek in it, because I don't think I'm going to give you the quiz today either with this type of formulas. It takes, I think it'd be like exam problem, not a quiz problem. So this exercise is, the chapter 8 is different. Chapter 8 has some nice things related to triangles. So in chapter 8, we're gonna learn how to deal with any triangle. So that'd be powerful. So you don't need right triangle, like on figure 1. You're gonna be dealing with triangles of with that contain any angles. So first section, I guess, deals with right triangle, Pythagorean theorem stuff. But following sections will deal with various other triangles. And actually, the exercise I just done should have been here in the section 8.1, because this manipulation multiplying by square root 5, dividing, that's what I had, like a similar figures. I think this exercise should be not in the previous section, but here in 8.1. So I think they mixed up location for the exercise. Sometimes it happens. Or maybe you can find some real sneaky way to avoid it, but I don't really think so, because it's times square root 5. So I just wanted to show you that there'll be two key, don't want to say theorems, but like formulas, or they call them law of sines and law of cosines. And those are, I guess, the most important in trigonometry when you deal with any triangle. So they will look at various triangles with no 90 degrees. Here, notice this is neither triangle with 90 degrees, because this is not 90. That's what we actually head into. And I hope that'd be exciting, because we never worked before with triangles that don't have 90 degrees angle, right? But it's rare when you have 90 degrees angle. Usually triangles can have any angles, right? So I think that'd be useful. That's the point. And I'm going to stop. So I'm gonna let you relax. Finally, you deserve it after all. So I'm gonna